Okay. Thank you very much. I think this is a bit of a change in pace because I'm an experimentalist, and we're going to be talking a lot about a certain experimental technique, which is neutron scattering. I would like it to be interactive if possible, so just ask questions as we go along. The topic, as mentioned, is fluctuating and disordered magnetism in insulating materials. It's the first of my 2 talks, so today will be strictly insulators, and I'll be thinking about systems where we can describe the individual spins as some sort of angular momentum, degree of freedom, and there are some interactions between them, and we can do the quantum statistical physics of that system. But we don't really have electrons that are moving around in the material, so it's strictly insulating materials. And tomorrow we're going to talk about semi-metals and metals and strong correlations and their magnetic properties. Today will also be a bit more heavy on explaining the experimental technique, and I think you'll benefit from that both for today and tomorrow, hopefully. Okay, so this is a picture actually from our campus, Johns Hopkins University, but to be quite honest, this is not quite how it looks today. It looks more like something like that or something. So it's actually no snow right now, but it could soon come. So it's pretty nice to be down here in Florida for the winter school. The birds were doctored in, and that's an oriole and things. So I'm not quite sure about those. But they stuck around for you. My talk is actually going to be in 4 parts essentially, and I'm maybe trying to pack too much stuff in, and so maybe I'll skip ahead if I see the clock is running, or if your reactions are indicating that. But basically, there are these kind of chapters of the talk. So first, a bit about experimental technique, then about what a local moment is in an insulator and how we can actually probe its properties with neutrons and other methods. Then we'll have these moments actually interact with each other, and that will be initially in a relatively standard case of a system that has a long-range ordered magnetic state, but there is some kind of interesting aspects of the particular material that I'm going to talk about here. And then towards in the 4th part, we're going to talk about entanglement and emergent quasi-particles, and that'll be reflecting our attempts to develop materials that actually form quantum spin liquids. Some of the things that we touch on today, we will also revisit a little bit tomorrow when we try to bring in itinerant electrons as well. Okay, so that's the story. There are a lot of people who have contributed to this work, and some of the kind of recurring individuals are here. Your organizers are both on the chart as well, and actually they made very important contributions to significant parts of this talk. The other thing I wanted to illustrate with this slide is that this is work that typically involves many different areas of expertise, including theory, and that will be one of my messages. This is a theory winter school, and the message that I would like to take across is that we really need your help, in fact. I mean, we have a fantastic experimental technique. We can probe many interesting details of correlated systems, in fact, more than we can explain, and there are a lot of interesting details that are just kind of dormant and in need of people to really think about them and learn about them. So theory is certainly an important component. Interesting materials come out of chemistry, so we have collaborations with Bob Carver's group, various people at Hopkins, Terrell McQueen, say at Copier, are growing wonderful materials for us. The instrumentation is pretty advanced and is constantly developing, so we have people from facilities who are involved in that. And these are the various funding sources, DOE, the Moore Foundation, and the various neutron scattering facilities, of which this one sadly has fallen off the web entirely, totally dormant, and we can't even get in touch with them. We had many experiments that were supposed to go on, and so it's really unfortunate. Anyway, hopefully it will soon be fixed. It'll be quite packed, this talk, so I just want to make a reference to various places you can read more about neutron scattering. There are wonderful books indicated here. And actually, there's a series of lectures that are recorded and available online that go through all the aspects of neutron scattering, much more than you probably need to know, but there it is if you'd like to take a look. Okay, so let me just say a few words about the scattering technique. I first want to introduce the thing that we're actually measuring, which is a scattering cross-section. And really the experiment is very simple, and it's always the same experiment in some ways. We're preparing a beam of neutrons with known properties in terms of momentum, energy, sometimes spin is controlled as well. We have it interact with the sample, and neutrons scatter from the sample. And we can say, what can we learn from that process? Well, we could look at the overall rate of scattering. That would be a scattering cross-section. It has dimension of an area. That would be quite dull because it's just one number, the overall kind of number of neutrons scattered per time unit. And so instead, we would typically resolve by direction the rate of neutrons scattered into a certain solid angle. And then we're talking about a differential scattering cross-section. But we could become even more specific and say, I want to look at neutrons scattered into this direction, and for that particular final energy, I could even control by incident and scattered spin state, and then I get progressively more advanced scattering cross-sections. And in fact, as the instrumentation is improving, we're getting more and more specific information by getting into greater detail in determining the state of the incident and scattered beam. Okay, now why do the neutrons scatter at all? It's because they interact with the material through two different forces, the strong nuclear force interacting just specifically with the nuclei. And actually that interaction can be described, because the nucleus is on the femtometer scale, it can be described like a so-called Fermi-Soda potential, just a Dirac delta function at the location of the nucleus. And the characteristic parameter that basically encodes the behavior of the individual nuclei, it actually varies very dramatically from element to element and from isotope to isotope, and that is actually an advantage for us experimentally, as opposed to for X-ray scattering, where the heavier elements are always just have larger scattering. In our case, sometimes very light elements can have a lot of scattering, so we can see hydrogen inside a heavy matrix quite straightforward. So that's the strong nuclear force, but what we're mostly talking about today actually is the interaction with the internal magnetic field of the material. So that's the interaction between the neutron and the electron. It takes place through a dipole-dipole interaction. And the important feature I want to bring out is that the corresponding cross-section for scattering is actually pretty similar to the nuclear cross-section. And that's very different from X-rays. X-rays can also do magnetic scattering, but there's a very large, it's a very, very small part of the cross-section, whereas in our case, magnetic scattering is as strong as the nuclear scattering. Okay, so I want to just make sure that you're fully aware of the scattering triangle, which we're actually always using and thinking about in these experiments. So let's just start thinking about the case of elastic scattering. This probes what I call the static structure, so the time-independent structure of the material is encoded or present, influences the elastic scattering. And actually, typically more than 90% of the scattering from a given material is going to be elastic scattering. Even though there is some inelastic part, most of it is just elastic. So in the elastic scattering specifically probes time-independent features. So that's why I'm saying it probes the static structure. Okay, so this is what the experiment might look like, Ki, Kf, and the scattering angle that we denote 2 theta, actually. And then we talk about the momentum transfer to the sample, which is incident momentum minus scattered momentum, and it's a vector pointing in this direction. And if you move these around, I get the wonderful scattering triangle, which has 2 theta as the scattering angle, and I can figure out the length of wave vector transfer, which becomes 2 times k times sine theta. So if I have a crystalline structure with a certain reciprocal lattice, then I can only have diffraction if this wave vector transfer actually matches a reciprocal lattice vector of the system. And if I denote that as 2 pi over d, then actually I derive from this what you might more directly associate with the Bragg's law, this lambda is equal to 2d sine theta is really just the manifestation of the nature of this scattering triangle. So that's elastic scattering. Now if we look at the actual scattering cross-section, so this is what I introduced in the previous slide, then that actually is a measure of the Fourier transform of the static spin configuration. So it's just written out in this expression. There are various factors that I think I'll skip for right now, but the key feature is this feature here, so just a lattice Fourier transform, and wave vector transfer becomes the conjugate variable to the position variable in the system. So actually the location of the, if I have a periodic structure, then this Fourier transform just has discrete wave vectors in it. So those are what we call Bragg peaks, and the location of those Bragg peaks are going to reveal the reciprocal lattice unit cell from which I can determine the real space unit cell. So that's what I get from just where I find the Bragg peaks. But the intensity of the Bragg peaks is going to reveal the underlying structure of the system, and in the case of a magnetic structure, then what I'm measuring is actually a vector structure factor, which takes this particular form. So I get information both about the magnitude and the direction of the spins on the lattice. Now, if I don't have a periodic magnetic structure, this expression is still good, but now the Fourier transform will no longer be constrained to have peaks at specific places in momentum space. I can have very broad patterns in momentum space, reflecting the lack of a translational periodicity. So that's the case of diffraction. Now I'm going to go to inelastic scattering. So as I said, it may be something like 10% of the scattering if I'm coming from a solid. If I'm going from scattering from a liquid, then all of the scattering is inelastic. But from the solid, it's just a small part that's inelastic. So now actually the scattered wave vector in this case is shorter than the incident wave vector because I lost kinetic energy to the sample. I transferred energy to the sample, and the energy transfer is just the kinetic energy of the neutron as it came in minus the kinetic energy when it came out. That's what we call energy transfer, and wave vector transfers as in the case of diffraction. Now you can see that this is the bisecting line, bisecting between these two directions. But now the direction of wave vector transfer has kind of rotated a bit because that's the nature of it. When this vector has gotten shorter, I can draw my scattering triangle again, and it looks like this. Now a long vector and then a shorter one. This is wave vector transfer. Still, this is 2 theta, my scattering angle. Now the length of wave vector transfer has this kind of expression, and you'll notice that wave vector transfer can vary in length. Oh, sorry. The length of wave vector transfer varies between the difference between the incident and final wave vector and the sum of the two. That's a very familiar expression. You can think about this as like a circle. So that means that as soon as you begin to transfer energy to the sample, then there will be a finite lower cutoff to wave vector transfer. I can no longer get to q equals to 0, actually. So it's kind of a exclusion zone just from the kinematics of the scattering process. Now, for inelastic X-ray scattering, you barely notice this because the wave vector is, because the energy is so large compared to the energy of the condensed matter system. So I'm talking about kilo electron volts, or at least hundreds of electron volt energies for the photons. So a little bit of transfer doesn't change the length of the wave vector very much. But for neutrons, the mass of the neutron is kind of similar to masses of collector quasiparticles in solids. So when I lose energy to the sample, I'm really also changing the length of the wave vector a lot. So I really have this exclusion zone at low wave vectors for higher energy transfer that I just cannot really get away from. That's inelastic scattering. And then to look at the corresponding scattering cross-section, this is the expression in its gory detail. And really, the main feature to point to is this so-called 2-point dynamic correlation function, S of Q and omega. And so I really am just measuring directly S of Q and omega. All of these other terms I worry about as an experimentalist, and they're also important if you're trying to simulate the data. And I'll just kind of mention briefly what they are. This is a so-called polarization factor, indicating that you pick out only the component of the dynamic correlation tensor which is lying in the perpendicular plane to wave vector transfer. You have to stare at it a little bit to see that. That comes from the dipolar selection rule. This term is a so-called form factor, which has to do with the fact that the spin density is distributed over the atom. And so it's not just a point dipole. And that'll cause the intensity to decrease as you go to higher wave vector transfer. So it's a rather boring function. It just kind of decreases a bit as you come out to 3 or 4 angstrom inverse if it's a transition metal. And then you have here the so-called Debye-Waller factor, having to do with the fact that the whole atom is moving about due to thermal or quantum quantum lattice vibrations, and that will also wash out the cross-section at larger wave vector transfer. And this is the overall scale for the magnetic scattering that we mentioned previously. Okay, so this is the thing that we can somehow access, and I just want to point out a couple of tools that we have to think about the dynamic correlation function. It helps when we look at the data. One of them is the well-known so-called detail balance statement that relates this function at positive and negative energy transfer. And so in some sense, you can say, well, I only need to measure at positive energy. Then, as long as the sample is in thermal equilibrium, then I'll know what value I'll get at negative energy transfer. So this sometimes in optics, they call it Stokes and anti-Stokes cross-section. So that's one part. Then we have various sum rules that are really useful to think about. One is that if I integrate over all momentum and all energy transfer, then I'm down to an equal time, equal position space feature. So I'm actually looking at the self correlation term at the same time, and that just becomes the total moment squared of that atom. So that means that in some sense you can think of our work looking at magnetic scattering as if there's a certain total amount of scattering which is present, and as we change the temperature of the sample or change the thermodynamic conditions in other ways, then this scattering is just going to move around in momentum energy space, but its overall intensity doesn't actually change. So it's quite useful to keep that in mind as you go through. Okay, the other thing is the equal time correlation function. That's related to the energy integral over the dynamic correlation function. That's kind of a snapshot of the spin configuration that you get from looking at that thing. So what we're going to be doing typically is that we'll be measuring the whole dynamic correlation function, and then as we look at the data, sometimes we'll develop from the data these other fiducials or indicators for what's going on in the material, including this equal time correlation function. You are probably, or you're well aware of the fluctuation dissipation theorem. It's also a very useful feature for us to look at, and I don't need to go through the derivation, but just this is the manifestation of the expression. And the reason it's important for us is that it relates two different physical quantities. This one is what we get from scattering, and this one is what, in principle, we can measure on a susceptometer. So I can literally go and do a PPMS, or physical property measurement system measurement of the magnetic susceptibility, and I can make a connection between what I measure in scattering and what I measure just in terms of the response function of the system. And so we'll be using that quite a bit. And tomorrow, when we talk about metals, sometimes it's useful to think about the generalized susceptibility of an itinerant spin system, and then we'll be using this expression to get from scattering to that function. There's another sum rule that's quite useful, the first moment sum rule, and it relates basically the energy-weighted integral over the dynamic correlation function. The left side here is a wave vector-dependent feature and relates it to a certain double commutator involving the Hamiltonian and the spin operators. And so this is actually a way that you can get essentially from the scattering, the inelastic scattering you measure, you can get to features that have to do with the ground state energy of the system. So we'll be using that on a couple of occasions. Okay, do you have any questions so far about all of those? Yes?
When you're talking about the sum rule, does it, like, the total intensity, will it be scaled by the local moment?
Yeah, by the dipole moment simply.
I mean, like the spin. Like, spin may not sit at the side, the entire spin. Like, for example, I think there was a paper in which they claim like only like 80%, around 60% of the spin sits on top of that.
Oh, and then the rest spreads out to oxygen or something.
Yeah.
Yeah.
The moment is not entirely on the top.
Yeah, when that happens, then there basically what I call the form factor now comes into play, and it will cut off. So what happens is that the dipole moment, which is leaked out onto the oxygen atoms, will be much harder to see because it sits in a more distributed orbital, and therefore it only is actually contributing to scattering at very, very low wave vector transfer. So it's as if you lose, it is in fact as if you lose overall spectral density by this process. Yeah, it's as if you just have less copper in there, or less of your 3D transition metal. So, but in fact, in these expressions, I had the form factor was in there. So if you cancel it out and appropriately, then in fact you are still measuring the total spin, including the stuff on oxygen. Another question is whether you can really do it practically, and very often that's not possible, actually. Yes?
So does it matter much if your magnetic moment comes from the spin or also the orbital moment as well, or does it just change the form factor?
It basically just changes the form factor. You're as sensitive to the spin part as the orbital part. The form factor will be different for those two contributions. It's good to think that you really are just interacting through the dipole-dipole interaction. So you're just sensitive. Whatever produces a dipole moment, you will detect it.
And are those, these might be really trivial questions from trivial physicists, theorists, but are all these form factors tabulated somewhere in a reliable fashion, or does it actually depend on the chemistry and the specific compound?
And they are tabulated. There's some really nice fat books in various places on the web. You can get form factors for most of the transition metals and rares. Not all of them. There's some that are kind of missing for good reasons. But the thing that the gentleman was mentioning there is typically not taken into account in those cases. So, so I think in some cases there might be quite interesting information about deviations in the distribution of the spin density present by looking more at the data than people typically do. Then I'd like to say a little bit about the methods, actually. Maybe it's been a long day and you had one yesterday as well. I just want to say a little bit about how we actually do the experiments. First of all, you need the neutrons, which are typically packed away inside the nuclei, and you can get them out by fission or spallation. Because of all of the energy that's released in the process of doing that, it's actually technically quite challenging to get a high flux of neutrons. You're just never going to get a flux which is anywhere near what you have for photons. Typically, you might get something in the range of 10 to the 8th newtons per second onto the sample in a monochromatic experiment. These are extremely low fluxes. But it has been developing over the years. This is the discovery of the neutron. These are high flux reactors intended for specialized scattering, specialized reactors for neutron scattering experiments. And then here is a new line which basically came up when dedicated facilities based on spallation came into being. And this is a different process where you have protons incident on nuclei from heavy elements, and you have a rather messy process that splits things apart and also has, through the process of spallation, a number of neutrons will actually come out, and less energy per neutron actually is generated in this process, which is a good thing, because in this case you're interested in the neutrons, not so much all of the thermal energy. So spallation is in a sense a source which has gotten a sharper rise, and that's part of the reason that you're seeing a lot of development in what we can actually do now using neutrons. So this is a picture of the NIST reactor, which is unfortunately shut down right now, but it really is a nuclear reactor into which tubes have been introduced so that the neutrons, which can sort of be siphoned off from the fission process, and then your instrumentation is sitting out here. Actually, it gets this dimension here is quite small. This is about one and a half meters or so, maybe 2 meters. So it gets very, very packed, and therefore it's quite useful to be able to bring the neutrons further away from the reactor using total external reflection and so-called neutron waveguides, or just neutron guides. And so this is what the NIST facility actually looks like. Some instruments are close to the reactor, and then a lot of more instruments are actually at quite significant distances, up to 30, 40 meters or more than that. This is a picture of the Spallation neutron source in Oak Ridge, Tennessee, and it's based on a proton accelerator and the spallation process, and inside this building is where all of the instrumentation actually sits. It's quite a busy place with all sorts of different experiments going on. And just to look a little bit more at the actual instruments, this is an old picture of, I think it's, I should know, Cliff Shull and Wedgwood, I think. And they're sitting at a diffraction instrument back in the probably 60s, I would say. Nowadays, there's a whole range of different kinds of instruments which are dedicated to solving and studying structures of materials using neutrons. They look very different depending on what range of wave vectors they're focusing on and what kind of sample geometries. Fundamentally, they're all essentially doing the same thing, which is what I described. This is Bert Brockhaus at the, I think it's a McMaster reactor, certainly in Canada. Well, it might be it's probably in Chalk River, actually. He's sitting at his triple axis machine. He was awarded the Nobel Prize in '94 for developing this concept of inelastic neutron scattering, also having the practicality of it demonstrated. And nowadays, there's, again, a whole range of different instruments accessing energies from microelectron volts up to electron volts. So it's really, again, great proliferation in capabilities. Fundamentally, they're doing the same kind of experiment. Another thing I want to really highlight is that as part of this whole activity, the key feature that we're looking at is interesting materials, and so it has to be closely coupled to an effort of developing new and challenging systems to look at, and also to be able to make large, high-quality single crystals. Here's a list of a bunch of crystals that we've been looking at in recent years, most of them grown by Sayed Copayer or Terrell McQueen, Johns Hopkins, also some of them by Bob Carver and company at Princeton. And so combining the high-intensity instrumentation and these kinds of high-quality crystals, we really can now, this is a picture of actually phonon scattering in iron silicon, not by myself. And what's shown here is the intensity as a function of 3 dimensions of wave vector transfer as a function of energy transfer. And you can see as you come up an energy transfer, the evolution of the dispersion surfaces having to do with phonons. So we really have access to this whole 4-dimensional 2-point correlation function. And it's really, for you theorists, I think it's going to be an interesting time to really begin to think about and be able to analyze those kinds of data. Okay, so that was the introduction. Do you have more questions about the sort of methods, techniques? Okay, so it's about half an hour left. I think this is actually a relatively short section, and then these are a little longer. So I'll probably go for about 5 or 10 minutes with this one. I just want to introduce how we actually can have and how local moments behave in insulators, and it's probably too abbreviated, but you hopefully have seen this kind of stuff before. And I will say a few words about how we actually learn by the experiments more details about the nature of the individual spin. So basically, we're talking about insulators, and the interactions that define the character of the local moment are really, I tried to list them here. There's an intraatomic Coulomb repulsion that somehow we associate with the name Hund, because his phenomenological rules describe the impacts of these intraatomic Coulomb repulsions. Then there is the crystalline electric field, which arises from the ligands. I'm thinking here again of insulators, and so those will be typically negatively charged, and they break the rotational symmetry otherwise that you otherwise would have for the partially filled shells of that atom. And then finally, you have a spin-orbit coupling. And as you go to heavier and heavier elements going from 3D to 5F, you're going to be increasing very dramatically the spin-orbit coupling. And so the whole way that these kind of interactions are organized in terms of their strength changes very dramatically across the series. You know, the rough thing that this could be discussed, and it varies like from particular situations, between situations, but this was sort of my general impression of things is that you tend to get stronger spin-orbit interaction as you go across the series. And so if I think of just the extremes of the 3D transition metal ions, things like chromium, iron, manganese, cobalt, titanium, etc., then you would basically have the Hund's rule establishes the total orbital angular momentum, the spin angular momentum, and then you have crystal field splitting as something which will actually lift the orbital degeneracy, so you end up with an orbital singlet. Sometimes there's a phase transition involved, a Jahn-Teller distortion, which will eventually produce this orbital singlet. And then the spin-orbit interaction comes in at the end, and it does introduce some anisotropy into an otherwise mostly spin-dominated form of magnetism. So relatively weak anisotropy, certainly anisotropic to some extent, but that's the situation there. And then if we come up to the 4F, which we're also going to talk about here, there actually the spin-orbit interaction is now typically has gotten stronger than the crystal field interaction. And so you're now letting the anisotropy is actually a perturbation on the total spin orbital angular momentum multiplet. And we're going to see an example of that particular effect in the next couple of slides. I'd like to mention that these 4D and 5D elements are particularly interesting because you actually get very anisotropic interactions as a result of the rearrangement of these terms here. And so that is actually the basis for realizing, potentially realizing Kitaev type physics in those systems where the spin-orbit interaction is significantly enhanced. And you've got this switch between these two, which actually leads to a more anisotropic exchange interaction. Okay, so then I'd like to just show you how you can determine these kinds of effects using neutron scattering. And I'll just look at the case of a rare earth ion, specifically neodymium in this case. And I won't really talk about the character of this particular material. It turns out it's a so-called Kagame lattice, and those compounds have a lot of very interesting physics in them. And I think I want to show you a little bit of the story, how you learn about the individual ion. And I also want to just really emphasize how important it is to understand which rare earth ion you're dealing with in a given context. They're going to be totally different as you go across the rare earth series because of the complexities of these crystal field effects. That's a relatively trivial thing on the scale of things. There's no kind of correlated physics involved, etc. But there's a lot of intricacy that can evolve from it. So it's really important to at least have that kind of worked out. And then you can think about the more interesting, like, correlated effects. So this is kind of homework that's really necessary. And neutrons are pretty useful for that. What's shown here is a false color map of the intensity of scattering as a function of scalar momentum transfer and energy transfer. So since I'm doing inelastic scattering just from the individual atoms, I'm not worried about their magnetic interactions between them, then momentum transfer is not a very interesting variable. The only thing that happens as I go with momentum transfer in this, on this scale of things is just that the intensity decreases due to the magnetic form factor. So that sort of identifies that these are magnetic excitations as opposed to some strange kind of phonon mode. That would be another possible explanation for these kinds of features. But because of the decrease in intensity, I know that it's actually magnetic scattering. Now, I've shown you I've sent you 3 different data sets from the same material. And what's changing here is the value of the incident energy, 40 millivolts, 80 millivolts, and 150 millielectron volts. And of course, I can't transfer more energy to the sample than the entire kinetic energy of the incoming neutron, because then it'll just stop and never gets to my detector. So I can, at the very most, transfer 40 millielectron volt when I come in with 40 millielectron volt neutrons. You can say, why don't you always go with 150 millielectron volt neutrons? That's because the energy resolution changes basically in proportion to the energy. So if I want really good resolution, I need to operate with somewhat lower energy. And so you can see that these particular 2 peaks, or these 2 modes, actually are the same as these 2, and then they show up again here and here. But it's only when I get to 150 millielectron volts that I get to see all of these various modes that are actually involved. And so what this is basically is that the J multiplet of the neodymium has been split into 1, 2, 3, 4, 5 doublets. There's a doublet ground state, and then there are 1, 2, 3, 4 doublet excited states. And these are all Kramers doublets. So this is a Kramers ion, and it will just have, in a sufficiently low symmetry, this is a very low symmetry case, I just get doublets coming out of that. And the way this is done theoretically is that you write down a crystal field Hamiltonian which has the appropriate point group symmetry. So you know the structure of the material well from diffraction. You've established the point group symmetry, and that tells you which of these tesseract harmonic operators are allowed to be present. And then there are these expansion coefficients that we might call B and M. Now these can actually be calculated just using the Taylor expansion of the Coulomb field generated by the ligand ions, and you'll get some sort of estimate for these parameters. But these are actually pretty bad estimates. They just give a very, very rough sense of it, the kind of the scale of the effects. And that's a good starting point, but it's pretty far from what you'll really see displayed in these excitations. So we need these energies to actually figure out what these parameters are in our crystal field Hamiltonian. This is the cross-section that we're measuring. And we can then go and basically, there's nothing which is not known about this. You know, these parameters can be put in. We can calculate the inelastic scattering cross-section. And that's actually what's being done here, comparing to the spectra. Now, this is intensity versus energy transfer. And for the 40, 80, and 150 millivolt, and you can see each of these transitions between doublets are present. And by tuning the parameters of the spin Hamiltonian, you can find your way towards an appropriate spin Hamiltonian to describe the impacts of these ligand fields. Then to see if it actually makes sense, you might want to do comparisons to other kind of data, such as susceptibility data. And here's a comparison to just regular susceptibility measurement. And that has some sensitivity to the same effects. And so without any adjustable parameters, you can more or less account for that. There's a little bit of, we discovered some low concentration of vacancies in this material. And then from this, you can actually predict what the anisotropic magnetization would look like just for a single ion. And this is actually, we don't have a measurement to compare that to, but this is the inferred anisotropy. And then you can also determine the eigenvectors of the system. And here's, for example, the inferred ground state, Kramer's doublet. The final fit has all of these parameters. So we really can know what the ground state wave function looks like for the individual ion. Now, just to put a editor's note in here, that's an important part of the story, but there's still something as important which is missing, which is knowledge about the interactions between the neighboring ions. That is actually a much harder thing to do. I won't get that from these kinds of measurements because my resolution was not appropriate. So I'm just seeing the individual ion. If I was to really, really zoom in with much better resolution to these things, I'm not sure that's technically possible, but then you'd in principle be able to learn something about the interactions between the ions. Okay. All right. Any questions so far on that story? Yes? This thing? Okay, that's an excellent observation. And basically what happens is that this line, the elastic line, is kind of a very, very noisy place because, as I said, 90% of the scattering is elastic. So everything which is solid in the vicinity of my sample will contribute right in this line. So I really can't say very much about that line. And I think there's some sort of background subtraction that took place here which produced this effect. You can see how it's kind of spotty. I think we had some way of trying to subtract off that contribution, but it's not working so great. So this is something you'll see in this kind of neutron spectroscopy. You'll always see a very noisy elastic line.
So in the lowest energy neutrons that you can use, what is the lowest energy resolution of any?
Oh, the best energy resolution. Okay, we can get to 1 microelectron volt, so 10 to the minus 6 electron volts. And so that's 0.001, so that's 10 millikelvin energy resolution. That's really just amazing. But it's not as if you could say, well, why don't you just go and do that? It'll be fine. The problem is that then I won't be able to reach these energy transfers at all. So there are all sorts of kind of challenges. But we're chipping away at it, and there are various advances.
For example, in the carbonic case, people are debating whether there is a spin gap or no.
Yeah.
You want to have that super small energy.
Yes.
Scale.
Yeah.
I'm just curious. Do you have it?
I'm going to show some data if we have. Let's see how I do. Okay, so actually, I wonder if I maybe, well, okay, we'll just see how it goes. If I run out here, I'll just begin the next lecture with it. So what I was going to mention here is I wanted to show you what happens now. I'm going to put these ions in, but I want a system which is not like totally novel. So I want something which has some sort of magnetic order and then so you can see the nature of the excitation, spin wave excitations, and so on, how that could happen. But I didn't want a totally boring thing, so I picked a compound which I'll also pick up on a little bit tomorrow. And so this is actually V2O3, but with a little bit of chromium in. And this is a very famous and interesting phase diagram. I'll talk more about it tomorrow, but basically along this horizontal axis, you are actually increasing Coulomb repulsion as you go left, decreasing it as you go right. And so there is a transition from an insulator to a metal as you change this Coulomb repulsion. And but what I wanted to focus on today is actually just the behavior in the fully insulating part of this phase diagram. And it turns out something quite interesting happens as you go from the paramagnetic insulating state to the antiferromagnetically ordered insulating state. It's actually a structural phase transition from rhombohedral up here to monoclinic down here. So it's fundamentally, you can say this is just some structural phase transition. The whole thing is changing quite a bit. Our argument will be that this transition actually takes place as a result of a very strong frustration which exists in the magnet in the insulating paramagnetic state. Turns out to be a very, very highly frustrated system. This is a new result that we've just recently went onto the archive. This is work by John Liner. Okay, so what's shown here is actually a plot in momentum space of inelastic magnetic scattering in two parts of momentum space. Bear in mind, we really have these four-dimensional data sets, and so we can't show all of the data, but we pick out certain things that we think are interesting. And what's shown here is data at 205 Kelvin, which is actually above the phase transition line, so somewhere around here. So this is in the paramagnetic state. So we've got these very broad structures, but they're not just, there are some pretty well-defined edges and things that are present. And actually that caught our eye because we've seen that in other frustrated magnetic systems, that they have these broad structures but with certain kind of specific features. And those tend to be associated with what I call satisfied local correlation, satisfied local constraints produce these kinds of very broad patterns in momentum space. Now, the question was, why does this system have these very, very broad pattern, even very close to the phase transition? So I'm sitting here almost going into the ordered state, but I have scattering everywhere in momentum space. It's really very strange, and we've actually considered that to be interesting for quite some time, and this is kind of what eventually came out of thinking about and working on this problem. So we collaborated with Rosa Valenti and Harold Jeschke and company, who have developed a fantastic capability of using DFT to actually calculate exchange constants in a number of different materials, including this V2O3 system. So these are all the kind of near neighbor vectors connecting sites, and this group went and calculated the exchange constants using DFT, LDA plus U, and they got these particular values of the exchange constant. Now, we don't have a way to really measure those experimentally directly. All we see is this diffuse scattering pattern. And so we asked ourselves, with these exchange constants, can we understand this kind of scattering pattern? And so Xu Zhang, who's at Johns Hopkins University, used what's called a Gaussian approximation that I'll talk a little bit about later as well, to actually calculate these short-range correlations based on the exchange constants. And she actually found, despite these relatively strong interactions, a pattern that's pretty similar to what we actually see experimentally. So we think that these are reasonable values of the exchange constants, and they do in fact account for this very, very short-range correlations. So then the question is, what is the kind of reason, the back of the envelope reason, that the correlations end up being so short in the system? And it turns out that that's actually because of frustration on the honeycomb lattice, or at least that's our explanation for it. Because it turns out if you look carefully at these exchange constants, then the dominant interactions are in fact between the near neighbor interaction that I call J1 and the next near interaction that I call J2. The compound itself is a stacked honeycomb lattice. However, the honeycombs are not ideal. They're somewhat puckered. So it is a complicated structure, but I'm trying to boil it down to its basics to understand kind of let's say, qualitatively why it has these short correlations. And it turns out that for this model, if I make J1 very, very large, so that's where the near-neighbor interaction is dominant, then I just have a honeycomb lattice, and that's just going to give me the regular antiferromagnetic structure in the honeycomb. It's a bipartite lattice, so there's no problem getting an antiferromagnetic order. If I go to very, very large values of J2, then I have actually decoupled triangular lattices, as indicated here. If I only had J2, then these would be kind of decoupled from each other, and I end up with this structure, which is really, a set of triangular lattices that don't talk to each other. I end up with this kind of structure. But in between these two, there is actually a state which is, I think, somewhat questionable what the actual state is supposed to be, but somehow very dominated by the competition between J1 and J2. And one proposal has been that there's a kind of a valence bond solid state that involves singlets forming on each of the honeycombs and then organized in this kind of fashion. So we think that, according to the calculations by Valenti and company, then we are quite close to the interface, or to the boundary between these two states. And we think that then this very, very broad patterns have to do with the frustration on this honeycomb lattice. One thing I should just point out is that the calculations I showed you previously here, they actually involve all of these exchange constants. We haven't made the approximation to say it's just a honeycomb lattice. But when we talk about it, I think that it simplifies things to think about the individual honeycombs, and they seem to be actually very, very frustrated. Now, to look at this transition then, if I start off with these kinds of patterns I saw in the paramagnetic state, and then I begin to cool down, as soon as I enter this monoclinic state, the features become very, very sharp, actually, in momentum space. This is in the ordered state, and then I come all the way down to low temperatures, and I have really, really sharp features in momentum space. These are all measurements at a finite energy transfer, I think it's 10 millielectron volts. So we're kind of cutting through the dispersion relations that you'd expect for antiferromagnetic spin waves. And so you can say, why am I having this phase transition occur? And to answer that, we have to really analyze the magnetic excitations in the ordered magnetic state. So I want to show you what happens to the inelastic scattering, now shown as a function of energy and momentum transfer. And this is what it looks like in the paramagnetic state, very close to the phase transition. So really broad and kind of dull-looking features. Then we cool into the ordered state, and we have very kind of actually pretty dramatic development of spin waves out of this morass. These actually will be things that we can analyze to obtain an experimental values for the exchange constants. And so what we did in terms of comparing to theory is that these are measurements of spin waves in the ordered magnetic state. Then we take the DFT calculated exchange constants, and we can calculate this kind of spectrum. It's not quite the same, but the bandwidth is pretty good, and many of the features are there. If we allow ourselves to adjust the exchange constants to have the optimal agreement with the data, then we end up with this kind of agreement, which is really pretty good. So it's a very complicated compound, a lot of exchange constants, and we end up being able to extract then a table of exchange constants here. So this is the paramagnetic insulating state where we have to rely entirely on DFT to obtain the exchange. This is the monoclinic state. This is the ordered structure. And then here you have all of the different exchange constants that we determined from DFT and then through the Neutron experiment. And the very, I think, significant feature that I wanted to point out is that every single of these interactions actually turns out to be satisfied. I have to explain what I mean by that, but satisfied in the ordered magnetic state. And what we can say is that here is shown the sign of the dot product between the neighboring spins connected by this exchange constant. And you see that these spins are actually ferromagnetically oriented or ferromagnetically correlated. Correspondingly, the exchange constant has a negative sign. So that's a ferromagnetic interaction. And then here we have an antiferromagnetic correlation, but then we also have an antiferromagnetic interaction. So at every single of these interactions is well satisfied. And that really contrasts with the situation in the paramagnetic insulating state where I had this competing near and next neighbor interaction. So what's happening, we think, at this transition is that I'm going from a very frustrated arrangement of interactions which actually does not point to a specific ordered magnetic state and produces this very, very disordered configuration of spins in the paramagnetic state. But then basically there's a interesting piece of physics going on at this phase transition where the a secondary state is assumed, which has a lower space group symmetry. It goes to a monoclinic structure that presumably costs some we could call lattice energy or structural energy, but correspondingly I'm now able to satisfy every single of those magnetic interactions. So this kind of transition is something that we think that we've seen in a bunch of different systems, in the sense that that there is this kind of interplay between the magnetic interactions and the structure of the system, where many times we like to think about those as decoupled from each other, and we say, here I have my lattice and it produces this frustrated magnetism. But what I'm saying and what this data indicates is that it's actually kind of an oversimplification to think of these things as detached, because there are situations in which the lattice kind of deforms, prior to actually developing, let's say, an interesting quantum spin liquid state or something like that, then actually the lattice is no longer able to deal with the frustration, and there's that kind of phase transition. So yeah.
So the question is, I think you partly answered it. Did the magnetism drive the fluctuating transition, or is it chicken and egg question?
Yeah, that's a difficult thing to, and you often get into sort of. I think both of those energetics are very important in this transition. So it's, and actually we've had a lot of discussions in the group and so on. But,
this is the first one, or best one?
yeah, it is. Yeah.
And is it possible to supercool?
Yeah, I think yes, it is. Yeah, it is. Not very much actually, and it.
Turns out that in better quantum organics, there is a very similar situation that happens. You have a very diffuse X-ray scattering and high temperature phase, very frustrated. Then it distorts, and then this is released.
Yeah.
But they were able to supercool, and then they actually find some kind of freezing without disorder, and this doesn't occur.
I see.
So it may be interesting.
Yeah, yeah. In some ways, you could say that the metal almost offers that. In this case. Okay. Well, I think we're sort of getting rather short on time, so I just want to. I want to just end and also leave time for some questions, and we'll talk more about the entangled magnetism at the beginning of tomorrow's lecture. But I just want to end with my sort of perspective and my message again, which is I think hope you can see that you can really do a lot of interesting physics using neutrons. We'll show you more tomorrow. There's a lot of progress now in the instrumentation. And actually, it's going to keep going, I think, for some decades. And a lot of the interesting science is going to actually come from progress in methods of data analysis and really connecting to very sophisticated theoretical work, both ab initio work, DFT work, DMFT, and also analytical work on correlated systems. All of this has to we feel that it has to really be brought in to enrich the physics that's being done. So I think there's great opportunities to advance quantum materials by really a closer engagement between theory and neutron scattering. Thank you for your attention.
Are there any questions for Collin?
Oh, those. Yeah, those are. The answer is that there is a lot of very interesting physics in those systems. Actually, from the Murigal group, they've been working on the dysprosium version of these and found something they call spin fragmentation, which is the coexistence of a short-range spin order with a long-range monopolar order. So the spin is broken. The idea is that the spin breaks into monopoles, and they actually order on the lattice. And then, but this order then coexists with a disordered spin configuration, and the data is quite convincing, actually. We've been working on some other versions of this. This family of compounds is, however, a little bit tricky because the energy scale is so low, so there's some limitations to what we can actually do. So a lot of this work is very much, this particular work, the energy scale in some sense doesn't really matter for the physics. Sometimes we work on a compound that has, 100 millielectron volt bandwidth. Sometimes it's 100 microelectron volts, and the physics can be quite similar, but the methods are quite different. And for this particular family of compounds, it's really pretty taxing to do the experiments.
How does doping affect the doping structure?
In which one?
In the vanadium chromium.
Okay, so vanadium chromium, doping of.
So the sample energy shift is on the doped side.
Yeah. So actually, that's this one shows. So basically, the kind of simplified description of it is as follows: is that so chromium has 3 3D electrons, and so that actually tends to produce a half-filled shell in the particular point group symmetry that we have here. So it becomes a site in your lattice which is difficult for an electron to hop to, because you actually have a big gap to the next state that could go in there. Whereas titanium is the other way around. It is a site where it's easier to hop to this site. And so the idea that has been sort of in the concept that's been proposed is that this is really like effectively reducing the Coulomb repulsion, and so driving in more towards a metallic state. And this is like increasing the Coulomb repulsion, and therefore localizing the electron, so it becomes a Mott insulating state. And so this phase boundary is the transition as a function of U over W, supposedly. But this is now really in development, because it turns out that, it's not really surprising, but in the vicinity of these dopants, there's significant havoc that's being generated, actually, and you really need to think about what things look like there. And there's been some DFT work by Rosa Valenti and company who actually look at that. And I think it's going to very much enrich the way that we think about this phase transition. I think this rough picture I initially mentioned is probably not really appropriate, and the kind of the electronics of these special environments where the dopant lies is going to be very important. It's some sort of localization effect having to do with those. So it's complex. But this compound, we live with it and we're interested in it because it's one of the very few compounds that actually has this kind of transition.
Okay, one more question.
Yeah, I mean, the phonons are there, and in fact, there's some features of this that we think are probably, it's not so easy to see, but yeah, so this is in the paramagnetic state. This stuff is still there, actually. And when you go into the ordered state, it seems to still be around. So there certainly are phonons in the system. We haven't ourselves really looked very carefully for that, but there's some recent inelastic X-ray scattering work that actually is looking more at those features.